welcome to properties of continuous functions. So again, the idea here is we would like to easily be able to determine if a function is continuous without having to necessarily graph it or carefully search for all the places it's undefined. So the idea, again, we would like a quick way to determine where a function is continuous. And so we'll have some properties as well as just some basic facts about specific functions that we'll regularly be working with. So for our properties, we have f and g are continuous on an interval I. So we have some interval I, here's I, C is somewhere within that interval, and f and g are both continuous on that interval, whatever they look like. So then we have the following are continuous on I. So we can take either the sum or difference of those functions. So the function f plus g and f minus g are both continuous on I. Constant multiple. If we take b times f, where b is a real number, then that will also be continuous. So these are continuous on I. So f plus g and f minus g are both continuous on I. B times f is continuous on I. Products, we can go ahead and multiply the function f times the function g, and that will be also continuous on the interval I. Quotients, the function f divided by g is continuous as long as g is non-zero on the interval. So it is continuous. Oops. As long as g of x does not equal 0. Oh, I just realized, I apologize. In this case, unlike the previous ones, we don't need c in our interval. C was just a real number, in which case I just used b instead of c. All right, powers. So for n an integer, if we take our function and raise it to the nth power, so meaning f times f times f times etc. Is continuous. Roots. If we want to find the nth root of f, for n a positive integer, this is defined or is continuous as long as f of x is greater than or equal to 0. For n even, for n odd, it's always continuous. So it's continuous on I for n odd. So again, this n was a positive integer in this case. And then for compositions, we're going to mix things up a little bit. We're going to change this so that f is continuous on I. With range equaling j. So the set of all outputs on interval I. And let's see that G is continuous on J. Then we wind up getting that G composed with F is continuous on I. So basically, because the function G, you're putting in F's output, you want it to be continuous on F's outputs instead of on the interval I. And from here, we're going to look at some special functions which will pop up regularly. So first, let's go with the following functions. Are continuous on their domains. So you don't have to prove the limit is equal to the function at every single point in the domain. You can just use this fact that these functions are continuous on their domains. So polynomials are continuous on their domain, which is all real numbers. So polynomials are continuous on all real numbers. Rational functions are also continuous on their domains. So polynomials, this is continuous for all real numbers. So the whole real number one. Rational functions is where the denominator does not equal 0. And then ones that we can't just use those rules we were working with, all of our trig functions. So cosine x, sine x, tangent of x, secant x, cosecant x, and cotangent x are all continuous on their domains. So once again, cosine and sine, we're looking at the whole real number line. Tangent x, we run into problems every time cosine equals 0. So for this, we just have that x is not equal to an integer multiple of pi. Oops, sorry, of, sorry, that's pi over 2, and it's the odd multiples. 2k plus 1 times pi over 2 gets us all those odd multiples of pi over 2. Right? Cosine 0 when we're at the top of the unit circle or at the bottom. Secant x, again, you can't have x be an odd multiple of pi over 2. Right? Cosine on the bottom. Cosecant x, is with sign on the bottom. And for that, we can't have an integer multiple of pi. And then cotangent also has sign on the bottom. And once again, we can't have an integer multiple of pi. So all of these I'm using k and integer. And then beyond this, the function a to the x, where a is greater than 0. Natural log of x. And both of those on their domain. So a to the x is for the whole real number line, as long as we're looking at positive a. Natural log of x, we're stuck with x greater than 0. And then last up, for our special functions, if we look at the nth root of x, here where n is a positive integer. So if n is odd, and this is the whole real number line. If n is even, then we're looking at x greater than or equal to 0. Again, n is a positive integer. So when we do these functions, you immediately know they're continuous on their domains.